In this video, we have a look at how to determine if a 2 by 2 matrix has an inverse, and if it does, what the formula is for that inverse matrix. Before we get started, let's have a look at the resulting inverse matrix formula based on the matrix for A, B, C, and D. We can see here that there's a fraction out the front. We'll have a look at how that fraction's formed and how the values within the matrix are determined as well. So let's start by setting up our inverse matrix. If we have a 2 by 2 matrix, which is expressed as A, B, C, and D, and we want to multiply it by another matrix such that the result is the identity matrix, which is the ones down the diagonal, then we'll start by labeling our inverse matrix as W, X, Y, and Z. What we'll do is we'll multiply those two matrices on the left-hand side together and match them to the entries in our identity matrix. So we start our multiplication by using the entries in the first row of the matrix on the left, multiplying it by the entries in the first column of the matrix on the right, and that gives us AW plus BY. We then go to the second column of the matrix on the right, and that'll give us the entry AX plus BZ. And then into the last row of our product matrix, which we want to be the identity, we end up with CW plus DY, and then the last entry, CX plus DZ. Now we want that product matrix to match the identity matrix, so we can see the matching entries here according to their colours. And what we'll do now is we'll solve these equations such that we're trying to find the values for W, X, Y, and Z. Let's have a look at how we go through that process. First up, what we'll do is we'll look at the first entry in both matrices. So we have AW plus BY equals 1. We then want to create another equation using W and Y, and we use that in the first entry of the second row, getting CW plus DY equals 0. And the reason why we do that is because we're going to solve these simultaneous equations for the values W and Y. So first up, what we'll do is we'll multiply both equations by values. We're going to multiply the first equation by D and then the second equation by B. And the reason why we do that is because then we have matching coefficients for the Y variable. And then we can subtract that and eliminate Y. So here's the resulting equations when we do the multiplications by D and B respectively. So now what we'll do is do equation 3 subtract equation 4, and we're left with ADW minus BCW is equal to D. We'll factorise out the W, and that leaves us with AD minus BC. And then what we'll do is divide both sides of the equation, so we get D over AD minus BC. So that's the value of our first entry. Now, whilst we don't know what A, B, C, and D are at this stage, when we do apply it to a known matrix, that will give us a W value, which is the first entry in our inverse matrix. Now, keeping the same equations, what we can do is find the Y value. So here's our two simultaneous equations again. AW plus BY equals 1, and CW plus DY is equal to 0. As we said before, we're trying to solve for unknown values W and Y. So this time we're going to eliminate the W variable. So we'll multiply the first equation by C and the second equation by A. That gives us ACW plus BCY equals C, and ACW plus ADY equals 0. We'll subtract equation 4 from equation 3, and that means that the W's will be eliminated, and we'll get BCY minus ADY is equal to C. We'll factorise out the Y, so we get Y outside of BC minus AD is equal to C, and then we'll divide both sides by BC minus AD. Now we can also express that as the same denominator as our first entry, and we do that by multiplying the top and bottom of our fraction by -1. So we get Y is equal to negative C over AD minus BC. Now for the next two entries, we're going to try and solve for X and Z. So our matching entry from our matrix multiplication is AX plus BZ is equal to 0, and CX plus DZ is equal to 1. This time what we'll do is we'll solve for z. So we'll try and eliminate x by making the coefficients in both equations the same for x. So we get acx plus bcz is equal to 0. That's equation 3. And we get acx plus adz is equal to a. And we'll make that equation 4. So now what we'll do is subtract equation 4 from equation 3. And that leaves us with bcz minus adz is equal to negative a. We'll factorise out the z. So that means that we get bc minus ad in brackets, all multiplied by z, and that equals negative a. And we'll divide both sides by what's in the bracket. So z is equal to negative a over bc minus ad. Now to rewrite that with the same denominator as before, we'll multiply top and bottom by negative 1. So we can express z as a over ad minus bc. And that's our entry in the second column of the second row of our inverse matrix. Now we'll use the same equations as we've just done in that previous entry, but this time to find the missing entry for x. So our first equation is ax plus bz is equal to 0, and then cx plus dz is equal to 1. And we'll multiply both equations this time by d and b respectively, and we'll do that to try and eliminate the z. So our two equations become adx plus bdz is equal to 0, and bcx plus bdz is equal to b. We'll label our equations 3 and 4 respectively, and this time we'll go equation 4 subtract equation 3 because we've got a b on the right hand side minus a 0, so we'll keep it positive. When we do that, we get bcx minus adx is equal to b, and our z's have been eliminated. So we'll factorise out the x and have bc minus ad in brackets. That all equals b. And then we'll divide both sides by bc minus ad. Now we can express that as negative b over ad minus bc to maintain our denominators with what's in our inverse matrix. And we can do that by multiplying both top and bottom of our solution for x by negative 1. So we can see here in the right hand side in red our completed inverse matrix in terms of the entries a, b, c and d from our original matrix. We'll take out the fraction 1 over ad minus bc because that's common throughout each entry, and we're left with d and negative b in the top row and negative c and a in the bottom row. Now that fraction out the front is significant because the value ad minus bc is called the determinant. And if that value is equal to 0, that means that no inverse matrix exists. So we'll label our inverse matrix a to the negative 1, and of course that's based on the matrix A, which is equal to AB in the top row and CD in the bottom row. If we compare our original matrix A to its inverse and just ignoring the fraction out the front which includes the determinant, you'll notice from the original matrix that the A and D value have been swapped, and the B and C have maintained their position, but they're now the opposite sign to what they were before.